In this video, we're going to be talking about the pH scale, what it is, how it works. We're going to put some common household materials on a pH scale so you can kind of get an idea. We're also going to talk about its related function, which is called pOH, and how it's related to pH. And then I'm going to basically give you a gigantic box that's going to help you correlate all the different equations that you can use to go between concentration of acid, concentration of base, pH, and pOH. You are going to need your notebook. You're going to need something to write with. I'm going to save the math for when we get into class, so you won't need a calculator for this. But once you have those things ready, let's go. So first thing I should probably start off by going over is a very special reaction called the autoionization of water. Water can react with itself in an acid-base reaction. Right? So one water molecule loses a proton, one water molecule gains a proton. So it can react as an acid and as a base. Now, at 25 degrees Celsius, the concentrations of both the H3O plus and OH minus ions are each 10 to the negative 7th molar. So what I'm going to do here is I'm kind of going to correct something that I told you in the first video for this chapter, which wasn't quite true. I said above 7 is basic, below 7 is acidic, and 7 is neutral. That's not technically the case. If H3O plus is higher than OH minus, it's acidic. If OH minus is higher than H3O plus, it's basic. If the two concentrations are the same, it's neutral. So you actually determine acidic versus basic by looking at the concentrations of these two ions, H3O plus and OH minus. Every solution will have both of them at the same time. They're just going to be in different amounts. All right, so let's get into what the P means in pH. P, just in mathematical terms, whenever you see it written, means to take the negative logarithm of that value. Now, for those of you who have had or in Algebra 2, you've already seen logarithms, so you know how they work, you know how the math goes for them. For those of you who haven't been in Algebra 2 yet, don't worry. I don't expect you to know how to do logarithm math. All I expect you to be able to do is press the logarithm button in your calculator properly. All right, so don't worry about having to know all that math. It's going to be fairly easy for what we need it for. Right, so when you see pH, that is the negative log of the acid concentration, H3O plus. If you see pOH, that's the negative log of the base concentration. So if you're taking the negative log of an acid, it's pH. If you're taking it of a base, it's pOH. Now for pure water 1.0 times 10 to the minus 7th concentration, pH is 7. If it's an exact power of 10, all you do is take the negative exponent, and that's going to be your pH value. Right? That's all a logarithm does. It just cuts off a bunch of zeros from a number. Now, an important relationship that we're going to need, right? So I'm going to call this equation 1. I'm going to call pOH equation 2. Here's equation 3. If you add up pH and pOH for the same solution, they'll always add up to 14. Right? So if my pH is 10, my pOH will be 4. So that's one way we're going to be able to convert between them. So if you have a strong acid or a strong base, all you do is take the negative log of the concentration, and that gets you pH or pOH, depending on whether it's an acid or a base. So let's go a little bit into the pH scale itself. So typically you see 0 to 14, right? Most things fall in this 0 to 14 banner. You can actually go below 0 and you can go above 14. For example, the concentrated acids that we purchase. So hydrochloric acid, when we buy it, is 12 molar. Sulfuric acid is about 15 molar. Those have pHs between -1 and -2. That's how strongly acidic they are. You can also get bases that go above 14. So you're not just limited from 0 to 14. It's just the common range where you see most things in your daily life. Right, but a couple things to keep in mind. Right, blood is actually very slightly basic, 7.3 roughly on your pH. Right, baking soda is a base, ammonia is a base, bleach is a base. Rainwater is typically a little bit below 6. The reason why is because it has CO2, which is acidic. Right, your juices, so orange juice, which is citric acid, vinegar, which is acetic acid, lemon juice, more citric acid, all of those tend to be below 7. Now, if I'm going to ask you to do a weak substance, like I said, strong substance, just negative log the concentration. Weak substances, though, don't break up 100%, so we need to account for that. The way that we're going to account for it in this class is I'm going to give you a percent ionization. All you do is multiply that by the concentration. Right? So if I say, for example, you have a 0.1 molar solution, and it has, we'll say, 10% ionization. Well, all I'm going to do is 0.1 times 10%, and that's going to give me 0.01 molar, and this is the number I'm going to plug in. Right? I'm not going to give you equilibrium constants to work with to figure out the exact number. I'm just going to give you these percentages. We'll go with it because the math is so much easier this way. All right, so that's how you deal with a weak substance. Now, we can go, so we've talked a little bit about going from concentration to pH, right? Just negative log the concentration. What if I want to go the other way? What if I have the pH or pOH and I want to know the concentration? Right? What we're going to do is we're going to undo the logarithm. Now, again, I don't expect you to know how logarithm math works. I'm just going to give you the equations. Right? So to undo the logarithm, the acid concentration is 10 to the minus pH. So I'm going to call this equation number 4. If we're working with a base, then we do the same thing for hydroxide, 10 to the minus POH. And we're going to call this equation number 5. Equation number 6 will let us convert between these two ions. Right? So this is going to be equation 6. The concentration of the acid times the concentration of the base is going to be 10 to the minus 14th. So what you can see is we have 3 sets of paired equations. Right? We have one equation to go from H3O plus to pH, which is equation 1. Equation 4 goes backwards. Equation 2 and 5 are paired. 3 and 6 are paired. So this is where we're going to get the idea that I call the pH box. Right, so the pH box, what I'm going to do is I'm just going to put in those 4 things. Right, so I'm going to say pH, and make sure you give yourself enough room to draw here because this is going to be a fairly large box. I'm going to have concentration of hydroxide. Remember, the bracket means molarity. I'm going to have concentration of H3O plus. To go from H3O plus up to pH, I'm going to do negative log H3O plus. Right, so pH will equal this. To go from OH minus to POH, I'm going to have POH equals negative log OH minus. Now just give me a sec to switch up my color here. We'll go to a blue for this one. To go backwards, to go from pH to H3O plus, I'm going to say that H3O plus is equal to 10 to the negative pH. And similarly, to go backwards here, I'm going to say that OH minus is 10 to the negative POH. And then we'll put in our last couple of equations, right? So to convert between these two, I'm going to say that H3O plus times OH minus equals 10 to the minus 14th. And to go between pH and POH, I'm going to say that pH plus POH equals 14. So I know this is a lot. These are 6 equations we're working with here. Realistically, what this is doing, this is saying if you start in any one of these 4 corners, you can get to any other corner just by using the equations to get you there, right? So if I give you the pH and I want to know the hydroxide concentration, I can either go across the top and then down, or I can go down the left and across the bottom. Doesn't matter which way I go, so I'm just going to do whatever math makes my life a little bit easier. All right, so this is pH and POH calculations. So a question that pops up might be, why do we use pH and POH to begin with? Right, so let's take a look at 2 different acid solutions. Molarity, concentration, doesn't do a good job of telling you how acidic or basic something is. Right? Vinegar's concentration, if we look at it, is 8 times more concentrated than hydrochloric acid is. Right? Vinegar is 0.8 molar, hydrochloric acid is only 1/10 molar. But even though it's 8 times more concentrated, vinegar is 25 times weaker as an acid than that hydrochloric acid solution is. Right? So 8 times the concentration, 25 times weaker. Doesn't do a good job of telling us the level of danger that we're working with. The other reason why we use pH and POH is, let's face it, the general public does not like working with scientific notation or numbers that have a lot of zeros for concentrations. Right? pH, because pH is basically 1 or 2 numbers than a decimal point, is a lot easier for them to grasp. So if I say, oh, lower number, more acidic, 1's less than 2.5. That means the HCl solution is more acidic than the vinegar solution is. It makes sense that way, and it's easy for people to actually recognize. All right, so that's it for pH and POH. In the next video, which, yay, the last set of notes for the year, we're going to be talking about a lab process called titration. If you have any questions, I will see you guys in class.